In the previous section, we talked about how the quote-unquote math of chemistry has to do with measurements. Now, the way we obtain measurements leads us to a discussion here about the reliability of such measurements. And there's two concepts we need to discuss here. One of them is accuracy, the other one is precision. Accuracy refers to how close is the measured value to the actual value that we're supposed to obtain. Precision refers to how close a series of measurements are to one another. In other words, how reproducible they are. When we communicate information about accuracy and precision, that is going to depend on the instrument that we use to make the measurement. And the level of precision is going to be preserved by using what we call significant figures. Significant figures are the digits in an instrument or measurement that the instrument or method is capable of reporting. Now, in the lab, we have majorly two types of instruments. Some we call digital, some we call graduated. Let's look at a digital balance here. Notice that the display shows us a value for the mass of this coin. The machine already has a built-in or calibrated accuracy and precision, and the display, the digital display, is showing us the total capability of this instrument. So when we record this mass, we have to report all the digits given by the displays. For example, in this case, I cannot simply say, oh, it weighs 5 grams. No, it weighs 5.01 grams. The instrument is designed to deliver that level of precision. The other type of instrument is what we call a graduated instrument. It is marked in intervals, and so an observer has to read them. So here is another object on a balance. Notice that in this case, the scale is not digital, but it's actually depending on some dials and knobs here. Let's see if we can read this. Notice that the bigger scale there has numbers 0, 1, 2, 3, 4. Those are grams. And you'll notice that each one of those ranges is subdivided into 10 intervals, which means that each interval is a tenth of a gram. If you look at where that little marker is over here, you can see that it is the pointer, and you have to read it. Notice that it is lying right between the 1.2 and the 1.3 markers on the display dial. So that means that I have to account for the fact that the measurement is somewhere in between there, and I had to inform anybody who reads my report that I could tell that the marker was not exactly on 1.2 nor exactly on 1.3. So I have to make a good estimate of where that lies, and this person estimated it at 1.27 grams. In other words, they reported to one additional digit. And that's the way we work with non-digital but graduated instruments. Some examples of instruments that are graduated: we have rulers, we have thermometers, and we have graduated cylinders to measure volumes. Whatever the instrument is, we have to record a measurement to 1 decimal place more precise than the smallest increment that the instrument can display. Let's practice measuring length. The metric ruler has divisions. The smallest divisions here are in millimeters. Now the numbers displayed are in centimeters, as you can see here on this ruler here. Notice that each increment, therefore, the smallest interval that the instrument displays is 1/10 of a centimeter, which is equal to a millimeter. So for example, these different measurements here, instead of 1 or 4 centimeters, could be read as 10 or 40 millimeters. This one here could be read as 11 centimeters or 110 millimeters. Now we need to adjust so that we can record with the actual precision of the instrument. So what would be the width of the blue rectangle here below? Remember, we need to make the measurement 1 decimal point more precise than the increments. So let's zoom in and see where the end of the rectangle falls. If the left end is placed exactly at the 0 centimeter mark, and we can see that it lies somewhere between 10.7 and 10.8 centimeters, or between 107 and 108 millimeters. Because the smallest increment here is 1 millimeter, or a tenth of a centimeter, that means that we have to record the measurement to one more decimal place. In other words, we would read this at either 10.76 centimeters or 107.6 millimeters. Notice that the digit that is in red here on this slide represents where the uncertainty lies. I mean, you could have chosen to call it 10.75 or maybe 10.77. Notice that you can't be arbitrary. It's obvious that the rectangle is falling somewhere right in the middle between 10.7 and 10.8 centimeters, or 107, 108 millimeters. So it would be inaccurate to record it as 10.71 because we can tell that it's not that close to the 10.7 centimeter mark. Now let's look at measuring volumes using graduated cylinders. One of the interesting properties of water is that it forms a curved surface at the top of the column. We call that curved surface a meniscus. These instruments are already calibrated for the presence of that meniscus, so the proper technique involves putting the graduate cylinder in a position such that the bottom of the meniscus is at the same level as your eyes, and that is the correct way of reading a volume here. Now let's say that we're using a 100 milliliter graduated cylinder. These are the ones you have in your lab drawers. Notice that again, the numbers displayed represent tens of milliliters, but each range is subdivided into 10 intervals or increments, which means that each increment is 1 milliliter. That's the smallest interval, the smallest increment the instrument registers. However, we have to record the measurement as one more decimal place. In other words, we're going to have to record these measurements to a tenth of a milliliter. Let me give you a few seconds to think about the one you have in here on the picture, and let's see how you would read that. Okay, it's between 36 and the 37 milliliter marker. I had to display my recorded measurement to one more decimal place. So let's say that we decided that's right in between. So we'll record it as 36.5 milliliters. Again, don't forget that to properly do this, you would have had to maybe lift the graduate cylinder up to eye level so that your eyes would be at the same level as the bottom of the meniscus of water. Let's do a little more practice here. I'm going to show you now a picture of a graduate cylinder. We're going to put some water in there. Let's zoom in and see where it is. What would be the volume of water in this graduate cylinder according to you? I'll give you a few seconds to think about it, and then we'll display it. Okay, let's say that the person reading this recorded it as 52.8 milliliters. That is fine. If you recorded it as 52.7, 52.9, that's fine. Notice that to the best of our ability, it doesn't look like the meniscus is exactly on the 53 milliliter mark. But if it were, you would be responsible for recording it as 53.0. Yes, even though in math, that zero past the decimal period would be considered as redundant, in our case, it's indicating the level of precision of our measurement. Notice that a guesstimate of 52.1 would not be accurate because it is obvious that the meniscus is not that close to the 52 milliliter mark. Let's try a 10 milliliter graduated cylinder. Again, let's put some water in there and let's see how this works. The 10 milliliter graduated cylinder has increments of 0.1 milliliters. That means that we have to measure things to one more decimal place. Let's look at a zoom in of this measurement here, and you can see that the narrower the tube, the more pronounced the meniscus. So the bottom of this meniscus seems to be, well, first of all, between 5 and 6 milliliters, but more precisely, more accurately, between 5.8 and 5.9. So let me give you a few seconds to think about how you would read this. Okay, 5.89, that is a good guess. You could have put in 5.88, or if you estimated that the meniscus was sitting right at the 5.9 marker, you would have to record it, as 5.90. Again, that zero is not redundant. It is significant. It's telling us what is the level of precision of this particular instrument. So let me give you some practice here. Let's pretend this is a scale here. It doesn't have units in it. But let's first of all establish what is the increment. In other words, what is the smallest interval displayed by the instrument? And then how would you read the measurement at position X and the measurement at position Y? I'll give you a few seconds to do that, and then we'll flash in the answers. All right, so the increment would be 1 unit. That means that your measurements have to be reported to 1 decimal of that. So X, 37.3 would be a good guess. Y, 31.0. If we estimate that it's right on the line, we have to add that 0. It is significant. Another instrument that is used in graduate scales are thermometers. In the old days, we used mercury, and mercury forms a convex meniscus. So in that case, you read at the top of the meniscus. In other words, essentially, the rule is that you read wherever the curve of the meniscus reaches an angle of 0 degrees. Now, nowadays, we don't use that. We use heavy alcohols with a dye in them. And so you don't have a meniscus anymore. You basically have a straight line there, straight surface. And you can read it applying the same rules that we just taught for measuring using the metric ruler and graduated cylinders. So let's see how precision and accuracy work with each other. Let's say that students were given a lead block, and it is calibrated to have a true mass of exactly 10.01 grams. So each student did several trials of measuring their lead block. Okay, the data on a table form is kind of hard to visualize. So many times what we do is we use, let's say, for example, in this case, a bar graph to represent the different students' measurements. Notice that what we have here is for each student, we have 4 trials. And for each trial, we put a bar equivalent to what is the mass they measured. The blue line represents what is the true mass, which is supposed to be 10.01. And then the broken line, kind of pink or red line, represents the average of the 4 measurements that each student took. The average is what is used to assess accuracy. In other words, of all the measurements, if I take the average, how close did I get to the true value? Notice that the student on the right, student C, obtained an average of exactly 10.01. In other words, this is a very accurate set of measurements. Not only that, but you can see that there's very little variation between the 4 trials that the student carried out. And so we would say that those measurements are both accurate and precise. Let's look at the student here on the middle, student B. Notice that it's interesting that this student had an average of 9.79 grams. In other words, their measurements were not very accurate. They were off of the real value of 10.01. However, what's interesting is that there's very little variation in the results that they obtain. In other words, although these students' values were inaccurate, there was precision in that set of values. It's interesting that they all fall under the actual mass of the lead block. If we look now at student A, you can see that both the average is off of what it should be, so these results are inaccurate. And also you see a lot of variation between the 4 trials, meaning that it's also imprecise. What is interesting though is that the values that this student obtained are all over the place. Some of them are above the average or the true mass, and some of them are below. So essentially what we're saying here is that we have 2 different kinds of errors. Students A had what we called a random error. It has equal probability of the values being either too high or too low. Now, student B, all of their values were underneath the target mass, the real mass. This tells me that there is a systematic error. There is a tendency towards all the values being clustered in one range here, and it indicates that there might be something wrong with either the instrument or the procedure. Okay, let's summarize then what we have here. Student A is representative of what we call random error. Student B is representative of what we call systematic error. So when we report a measurement, we want to convey 3 things in the information. Number 1, the value. Number 2, the units of measurement. This is important. And number 3, the certainty. How certain are we about the accuracy and precision of this instrument? The certainty is going to be indicated by the number of significant figures that we put in here. Now, the greater the number of significant figures, of course, the greater the certainty we have. In other words, if I report a measurement as 12 grams, that gives a lot, some margin of error that if I use an instrument or a measurement that said 12.05 grams, that tells me that I am certain of that measurement all the way to the hundredths of grams, not the single units of grams. You can see how that would give me a lot more certainty and an expectation that any variations I have, right, in further measurements are going to be confined to the hundredths of grams of mass. Now, all of these things we've talked about represent situations where you are the one recording the measurements. What about if you are reading a report where somebody else is giving you their recorded measurements? How do I establish the certainty in that person's set of values? Well, we need a method for counting significant figures, which by the way, we sometimes abbreviate as sig figs. You may have learned different ways of doing this in previous classes, so I'm going to show you the way I do it. You're welcome to use my method, you don't have to, but it works most of the time. So what I'm going to do is I'm going to look at a number and I'm going to decide on 2 scenarios. One scenario, the decimal point is present. Another scenario, the decimal point is absent. If the decimal point is present, what I'm going to do is I'm going to start from the left of the number, and beginning with the first non-zero number, I'm going to count all of the numbers as I scan from left to right. And that includes zeros. If the decimal point is absent, I'm going to start from the right side of the number. I'm going to start scanning from right to left until I reach my first non-zero number. And then everything going to the left is going to be counted as a significant figure. Be aware that when numbers have ending zeros and no decimal period, some authors, some people will consider that as being essentially non-specific, or there's different words that they use, but in other words, they'd rather not count significant digits. I like to count them because I want to assume that the person who made the measurement is trying to tell me, based on their number, how certain they are of the measurement they made. So you can follow these rules. Of course, these are just words. Let's do a little practice here. First of all, let's consider some specific situations, some special situations. If a number is in scientific notation, we're only going to take into account the coefficients digits, not the exponent. So only the coefficients digits are taken into consideration when calculating significant figures. If you want to make some non-decimal trailing zeros significant, what you can do is you can insert a decimal point. For example, the number 360 at this point is only significant up to the tenths of units. You know, the 3 and the 6, that 0 would not be significant. Again, some authors, some instructors would say simply, well, that 360 is ambiguous. But I prefer to say, well, I'm going to put two sig figs on it, the 3 and the 6. But let's say that I want to report that it was exactly 360. In other words, if it had been 361, I would have been able to tell the difference. I can do something that your math professors might consider heresy, and it is to put a decimal period next to that 0 with nothing afterwards, because now it forces me to apply the rule where I am going to count from the left to the right. I'm going to scan from the left, and that means that 0 gets included in my scan and it gets counted as a sig fig. Let me give you a few seconds to practice with each of the following measurements. How many significant figures are in each of these measurements? All right, 24 milliliters, very good, that'd be 2. 3,001 grams, right, that'd be 4. 0.0320 cubic meters. Again, if you follow my rule, you go from left to right because there's a decimal period, and beginning with the 3 and scanning to the right, everything counts, so that will leave us with 3 sig figs. Next one, 6.4 times 10 to the 4 molecules. We only count the coefficient, right, the 6.4, so that'll be 2 sig figs. Now the next two give you an example of what I just said earlier. The first value, 560, doesn't have a decimal period, so I'm going to count from the right to the left. My first non-zero digit is the 6, so that means that only the 6 and the 5 count, so there'll be 2 sig figs in here. Be aware, again, let me repeat this, that some instructors, some authors would simply say that it is ambiguous. It is not clear what the value, how many sig figs there really are here. However, if I want to look at the next one, this is where somebody decided they want to make sure I know that that 0 is significant. So they put a decimal period next to it, which means that now it's 3 sig figs, right? Notice that I could have also done this by writing that number in scientific notation. I could have written it as 5.60 times 10 to the second power. Very good. And that would also make it have 3 significant figures. Now, let's go into some specific situations here. Here is a ball bearing, and I have a ruler next to it. What would be the diameter, and what would be the circumference of it? Well, let's look at this. The diameter essentially is the distance from one point on the circumference to the exactly opposite side along the center, right, along the radius. So let's say, for the sake of illustration, that we read this as it's between 2 and 3. It's past the 2.5 mark. We had to add 1 decimal, right? So let's say it's 2.7 centimeters diameter. Now, would I be accurate in reading this as 2.1? No, right? Because the 2.1 mark would be somewhere out here, and it's obvious that that is not correct. In other words, remember, we are estimating this decimal digit, but it is not an arbitrary decision that we make. We try to make a good estimate. Okay, so let's see. How do we calculate the circumference? Well, let's say the formula would be diameter times pi. So if I put my calculator 2.7 centimeters times pi, I'm going to get 8.48230016 centimeters. That's on my calculator, which is capable of displaying 8 decimal digits. Now, can we really accept this level of precision? If the value that we measure was good to only one decimal place, it is not correct to say that we can calculate the circumference to this level, this magnitude of precision here. And so therefore, we have to now decide how many digits do I display on a value that is obtained from calculations using measurements. So let's look at the rules here. There's one set of rules for multiplication or division. The number of significant figures in the result is set by the original factor that has the smallest number of significant figures. So let's say I do this calculation on my calculator, right? And I obtain that value that's in there. Notice that 4.51 has only 3 significant figures. That means that my result has to be rounded to 3 significant figures. So the 1 stays, the 6 stays, and one more digit, 16.5, that would be the rounding. Remember, the next digit after the 5 is less than 5, so we're going to keep it the way it is. Let's look at an example with division. 6.8 divided by 112.04. That's the number my calculator says, but notice that the number on the left here only has 2 sig figs. That means that I need to round this to 2 sig figs. My first sig fig would be that 6 over there, and that means that I can go forward and I have to count one more sig fig. That would be the 0. The next digit is a 6, which means that I have to round up, and so I'm going to round up to 0.061. And of course, I'm not putting them here, but presumably these would have been measurements and they would have units in them. So we're just using numbers now to practice. For addition and subtraction, we have a different set of rules. What we're going to do is the result is going to carry the same number of decimal places, not sig figs, decimal places, as the quantity with the fewest decimal places. So here are 3 operations. The first one's a sum. The second one is a subtraction. And notice that one of the things that I did to help myself visualize it is I line up all of the decimal periods of all the numbers so that I can draw a line next to the number that has the fewest decimal places. In the case on the left, that's the 0.07 number, which only has 2 decimals. Notice that that line, when I extend it down to the result, tells me where I need to cut off my calculated value. So 5.4125 is going to have to be run to 5.41. Only 2 decimals allowed. In the case on the right, we can see there's only 1 decimal allowed. That's where the line falls. But because the next digit is bigger than 5, we're going to round it up to 5.7. Again, let's look at some special situations. How many pennies do I have in here? Okay, you're going to say 7. How about if I counter and say, well, how do you know that it's not 6.8 pennies? How do you know it's not 7.1? Well, no, this is an exact count. A number of counted objects is considered to have an infinite number of significant figures. Things that represent counting of objects are exact. We don't have to worry about sig figs. How many students are enrolled in Chem 1A? 72. Oh, professor, are you sure it's not 71.7? No, because there's no such thing as 0.7 of a student, right? Although some of you might feel like, hey, I'm only 50% there, man. I'm a 0.5. No, you know what I mean, right? So any number of counted objects is considered to have an infinite number of sig figs. Another one, how many eggs in a dozen? Well, by definition, a dozen is 12, right? So you would not come and argue, well, it depends on my measurement here. It could be 11.8 or maybe it's 12.5. No, because A number that comes from a definition is also considered to have an infinite number of significant figures. All right. So when I say a pair of shoes, that means two. It's exactly two. When I say a yard, well, that's exactly 3 feet. When I say a kilogram, that's exactly 1,000 grams. These are amounts that are defined, and therefore we don't have to account for sig figs in those kind of numbers. So let me see how this plays into calculations, right? We have these two situations. When there's a number of counted objects, when there's a number that comes from a definition. So this is why it's important to indicate the units, because when we're doing a calculation, we have to assess, is the number I'm dealing with an exact number or is it a measured amount? For example, let's say students measured objects and they have three different measured lengths: 6.64, 6.68, 6.70. They forgot to put the units here, but let's say that these are centimeters. What is the average? Well, the average, of course, is you add up the items and then you divide by the number of items. Your calculator says 6.67333, and the students average it to 6.67. Wait, why did they not average to 7 if this number here only has one sig fig? No, it doesn't. See, because that number 3 came from the number of items that we had, which was 3. It's an exact number, and therefore it doesn't. It is not considered into the counting of sig figs. So now what we have is just the top part of that operation, which is a sum. And because it's a sum, we round it to the number of decimal places, which is 2, and therefore you get an average of 6.67. Notice that the average matches whatever the method of measurement was for those three values. So it works out. When we round things, again, you may have learned different things. I keep it simple. Whenever you're rounding significant figures, let's say you decide what is the digit that I'm going to keep, and I look at the next one, the one I'm going to drop. If it's 4 or less, I'm going to keep the digit I have. If it's 5 or more, I'm going to round up. So for example, let's say I have 4 values here. I'm going to round to 2 significant figures. 5.37. 2 sig figs means I'm going to keep it at 1 decimal place. The next digit, 7, is bigger than 5, so I'm going to round it to 5.4. 5.34, the digit I'm dropping is 4, so I keep it to 5.3. 5.35, again, it is 5 or more, so that means I'm going to round out the 5.3 up to 5.4. And the last one, 5.349, rounds to 5.3 because I'm only looking at the digit that is next to the one that I'm going to keep. I'm keeping the first decimal here. The next digit, 4, is less than 5, so I'm going to keep it at 5.3. Okay, the last one here is what happens if you have multi-step calculations? The convention is that we are going to keep all of our numbers in our calculator and do the rounding at the final answer. However, although we don't round intermediate steps, you have to keep track of the sig figs, perhaps by underlining the least significant digit. So let's look at this operation here. Notice that it has a multiplication and then in parentheses a subtraction. Okay, the rule is let's do the operation in parentheses first. 5.489 minus 5.01 gives me 0.479. That's what the calculator says. Now, remember, if I had done just that operation, because the 5.01 only had 2 decimals, that 0.479 should have been rounded at the second decimal place in here. So technically, it would be rounded to 0.48. But I'm not going to do that right now. I'm going to keep the number in my calculator so I can then multiply times 5.903 times 6.78. But bear in mind that as that number goes into that multiplication, it's supposed to bring only 2 sig figs. That means that this result that I get here can only be expressed to 2 sig figs, and therefore we're going to round it to 19. Okay, just to wrap it up, please review these rules, and as you do the activity that we've called Experiment M, you'll get a chance to do some counting of sig figs, some rounding to appropriate sig figs, and then to do some operations where you had to keep track of the sig figs in your calculations. For the moment, this looks like just a set of rules. But please don't get trapped in just the rules. Remember, what we're trying to do here is to respect the levels of accuracy and precision of the instruments and methods that we use to make measurements, so that when we write a report of an experiment, anybody who's reading that can be informed as to what was the level of certainty in our measurements. All right? Well, that's it for now. In our next section, we're going to talk about how do we convert between one system of units and another system of units. I'll see you soon.